In the last unit of this topic, we looked at ionic bonding. Today, we're going to move on to a different type of bonding, covalent bonding. By the end of this unit, you should know what the covalent bond is, what it's formed by, what single, double, and triple covalent bonds actually involve, that bond length decreases with bond strength increasing as the number of shared electrons increases, and that bond polarity results in a difference in electronegativities between bonded atoms, and you should be able to deduce the polar nature of a covalent bond from electronegativity values, which we've already looked at. So what is covalent bonding? Well, a covalent bond, as you can see from the diagram here, is an electrostatic attraction between a shared pair of electrons and a positively charged nuclei. Okay, so negative charges of the electrons are going to attract each other, whereas you're going to get a repulsion between the positively charged nuclei of two different atoms. Okay, and you can see that here by looking at the charge density. You can see there's lots of positive charge density in the nuclei, and that spreads out. Now these electrons are called the bonding electron pairs, okay, and these are the electrons actually involved in the sharing between the two nuclei, and electrons not involved in bonding are called non-bonding electron pairs. Kind of makes sense because they're not involved in bonding. So there is a spectrum, which I did mention last time, between being a bond being 100% covalent and a bond being 100% ionic. Okay, so bonds fit between this continuum. Okay, and with an increasing difference in electronegativity, which is what this means, you're going to move more towards the ionic part of the spectrum, and also with increased polarity between the two atoms, you're going to end up with more of a transfer of electrons rather than a sharing of electrons. So you can see this illustrated here in the diagram. Okay, it's known as the Van Ichael-Ketelaar triangle of bonding. Okay, so we have, from last lesson, we calculated some electronegativity differences between the two bonding atoms. Okay, so if a difference, for example, is 0, and the average electronegativity, which is going to be the electronegativity of one atom plus the electronegativity of another atom divided by 2, by the other atom divided by 2, then that's going to be the average electronegativity. And on this axis here, we have the percentage of a covalent compared to the percentage of ionic. So as you can see, if the electronegativity difference is large, and if we go across to this part of the graph, the covalency of that bond is rather small. And correspondingly, if the difference between the electronegativities are low, then they're going to be 100% covalent. But we also must take into consideration the average electronegativity, and that's going to be this calculation here, and that's going to also decide whether it's going to fit within the covalent or polar covalent or even metallic continuum. Okay, so let's now look at a problem, which is more ionic, sodium chloride or lithium chloride? Okay, and we're going to use the diagram that we used on the last slide, and also our data book, because our data book has all this information. Right. So the change in electronegativity for sodium chloride is going to be the difference between the electronegativity of sodium, or maybe chlorine, minus the electronegativity of sodium. Okay, so it's going to be 0.9 minus 3.2, so about 2.3. It's the magnitude anyway, so it does make a difference. That's what those square brackets mean. So it's going to be about 2.3. Okay, so that's going to put it around about here on the continuum. Okay, here. There we go. And the change, or the average of sodium chloride is going to be, again, the 0.9 plus 3.2 divided by 2, 2.05, so around about here. Okay, around about here. Okay, so it's going to squarely into the ionic. Okay, so it's, if we plot that, it's going to be about there. Okay, so that's going to end up around about there for sodium chloride on that particular diagram. And if we look at the difference in electronegativity for the atoms associated with, or the ions at least associated with lithium chloride, it's going to be 2.2 this time, and the average is going to be 2.1 for the different electronegativities of lithium and chlorine, which puts it slightly below it, okay, there. So you can see from the diagram that sodium chloride is going to be more ionic of those two particular ionic salts. So we've also looked at this briefly in previous topics already, but we'll just reinforce it again. So polarity is also an important determinant. So the partial positive charge is written as delta plus, okay, so this sign here, that's delta plus, and the partial negative charge is written as delta minus lowercase d in the Greek alphabet. And the overall charge is called a dipole moment. Okay, so that there is known as a dipole moment and represents basically a vector where the charge lies. Okay. So in terms of polarity, just because a molecule possesses polar bonds, it does not mean that the molecule as a whole will be polar. So the example here we have carbon dioxide. Okay, so the CO double bonds are both polar bonds. However, the two dipole moments cancel out because they're going in opposite directions. So it's kind of linked to vectors like we have in physics. Okay, so because those two dipole moments cancel out, the compound as a whole, carbon dioxide, is going to be non-polar. In terms of polarity, as I mentioned in the previous slide about cancelling out and things, the molecule is polar if the electron densities are not symmetrical, such as there is a net dipole moment. Okay, so here we have the OH bonds being polar, okay, but they don't cancel out because they're the molecule is not symmetrical. The overall dipole moment is going to be a sum of those dipole vectors, and it's going to mean that water as a whole is a polar compound. It has a dipole moment. Okay, so looking at some molecules and whether they are polar or non-polar, or the reasoning behind it. Okay, so if we look at hydrochloric acid, or HCl gas maybe, it's clearly polar because there's only one dipole moment. Carbon tetrachloride, this guy here, which we'll learn more about when we do organic, it's going to be non-polar because the dipole moments cancel out. This one cancels out that one. This one cancels out this one. Due to the symmetry of the trigonal planar, they're all going to have 109.5 degrees. Okay. Ammonia, this guy here, is going to be polar because these two cancel out, just leaving this one dipole moment. It's interesting comparing and contrasting, say, chloroform. So this guy here is really electronegative, the chlorine, so it's going to be a very strong polarity. So although these two cancel out, due to the strong electronegativity of the chlorine, this dipole moment here is a lot bigger than this guy here. So they don't cancel out. So that means that due to that extra chlorine and a lack of symmetry, then chloroform is going to be polar. And boron trifluoride, again, due to the symmetry, they're all 120 degrees. This guy is going to be non-polar. The dipole moments all cancel each other out. Okay, so looking at bond strengths, each bond contains at least two electrons. Okay, so for hydrogen, you've got one hydrogen shares one electron, the other hydrogen shares the other electron, so single bonds essentially are just a sharing of electrons. Triple bonds are shorter and stronger than double bonds. It requires more energy to break them. And double bonds are shorter and stronger than single bonds. So far, so good. And this is just illustrated here by the bond energies. So, for example, a hydrogen-hydrogen single bond requires 436 kilojoules per mole to break, and it's rather short. Okay, and the oxygen-oxygen double bond requires a little bit more, and it's short as well. But I guess looking at the carbon-carbon double bonds really illustrates the difference in bond strength between single, double, and triple. So single bonds are 364. Okay, carbon-carbon double bonds are about twice as much as that, and carbon triple bonds are about 3 times as much as a carbon single bond. And you'll see the bond length also decreases as you go down. Okay, so that it decreases as you go down, whereas the energy required to break goes up as you go down. Okay. So looking at bond strengths, a strong attraction between two nuclei for electrons creates a short bond length. Therefore, the short bond lengths have high bond dissociation enthalpy. Okay. So ionic bonding, in summary, is electrostatic attraction between positive and negative charges, whereas covalent is electrostatic attraction between shared pair of electrons between atoms, and metallic is the electrostatic attraction between a lattice of positive ions and delocalized outer shell electrons, which you would have learned last year. Ionic bonds, the smaller the ions, the greater the charge in the ions, the stronger the attraction. Okay, so magnesium 2+, stronger than sodium plus, interacting with chloride, and this is due to a greater charge density. Okay, and in covalent, the shorter the bond, the stronger a bond. Okay, double bonds are stronger than single bonds, triple bonds are stronger than double bonds, and so on. And in metallic, the smaller the metal ions, the greater the charge in the ions, therefore greater number of delocalized outer shell electrons there are, and a stronger attraction between the ions and electrons. Because again, it's basically charge density. So that's the beginning of covalent bonding. The next topic, we will look at the giant covalent network solids, which I'm sure you've already been familiar with from last year.